All right, so let's crack into the problems. So this one is actually very similar to one of the final exam problem that came out a year or 2 years ago. Um, that one is based on the smiling emoji. This one's slightly different, but the idea is pretty similar. So we have laminar flow. That's important information because then that gives us an idea of which drag coefficient equation to use already. Uh, they're asking us when we have one plate and then we duplicate into four in different arrangement, either as a bigger rectangle, sorry, a bigger square or a rectangle, how would the drag basically change? It doesn't quadruple. The area quadruples, so the area here is the same. So that's A. This whole thing becomes 4A. This one is also 4A. So it's very tempting to go like, oh yeah, the drag force just quadruples. Not quite. Each of the length, so we're going to call them L. In this case, that is 2L and that is 4L. That's going to go in and change our drag coefficient because the CD is a function of your Reynolds number, right? RE is equal to rho UL divided by mu. If your L changes from L to 2L to 4L, that also changes your Reynolds number and drag coefficient. So start with the one block. That one FD equals half CD rho V squared A. Pretty straightforward. CD is equal to 1.328 drag coefficient divided by square root of RE. Again, this will either be provided in your crib sheet, or if you're allowed to have an A sheet, then I recommend just bring it in. Remember, this only works for flat plate in laminar flow. If it's turbulent, you're going to use the other equations. RE is equal to rho UL divided by mu. So sub the Reynolds number in, you're going to have your CD equals 1.328 divided by square root rho UL divided by mu. We can't quite calculate it, so we're just going to call it a constant. The idea is that later on when you have more plates, this is just going to multiply or basically change how the constant of the drag coefficient. Um, so that gives us FD of one single plate equals half constant rho V squared A. Now let's move on to configuration A with your four plates as a bigger square. Again, FD half CD drag coefficient rho V squared A. CD equals 1.328 divided by square root RE. Now, however, your Reynolds number has actually changed because we're double the length. So RE is actually equal to rho U 2L divided by mu. Sub it into your CD, your drag coefficient becomes 1.328 square root 2 rho UL divided by mu. We're gonna calculate the square root 2 and just basically take it out. So 1 divided by 1.414 equals 1.3, or sorry, not equal. Multiply that times 1.328 divided by square root rho UL divided by mu. So this is the same as your constant from before, right? So all you just gotta do is just 1 divided by 1.414. And the drag coefficient for configuration A becomes 0.707 times your constant from before. Now you actually plug it back into your drag coefficient equation. So FD is equal to half times 0.707 constant, rho v squared A becomes 4A. And that's going to give us basically 2.828, which is basically just 0.707 times 4, and then the rest of it stays the same. And the recording panel is not letting me change the color back. There we go. 1/2 constant rho v squared A. So the drag force only can roughly triple when you have 4 plates, right? It didn't actually quadruple. Now, when you actually compare it, now let's finish it with the second configuration, configuration B as a 4 square and forming into a rectangle. So for configuration B, FD equals half CD rho V squared A. Again, we have to update the drag coefficient. Your Reynolds number has changed yet again, because now the new length is 4L. So RE is equal to rho U 4L divided by mu. That's going to give you a drag coefficient of 1.328 divided by square root of 4 rho UL divided by mu. Take the square root of 4 out. That gives you basically 1 divided by 2 times your constant as before. The next step is just basically plugging it back into your FD. So 1/2 constant rho V squared, again 4A, don't forget. And that's going to give us 5 times 4, 2 times half constant rho V squared A. Configuration compared to configuration A. So let's quickly walk through what we've done here. So we found a drag for 1 square plate, and then we basically redo it for a configuration A of having a rectangle of 4, or configuration B, having it. So configuration is a square of 4 and configuration B as a rectangle. Every time we change the geometry, we have to recalculate the drag coefficient because our length has changed, right? So the length changes, so we have to update the Reynolds number to update our drag coefficient. We don't have the values to calculate majority of this, so we have to basically keep it as constant, right? And then going from there, we basically just comparing how the drag force updates, which in this case, when you have it as a rectangle, the drag force roughly triples. But when you have it as a rectangle, the drag force only double. So funny enough, having it in configuration B, you get less drag compared to configuration A. Now you're still going to get more drag than your baseline one single square. The reason is and this is quite realistic, when your flow first hits the beginning of the plate, there are more drags there because of the way the boundary layer is, right? So the boundary layer is a function is a function of x, or basically in this case, your length. So the further it goes, basically the near wall effect, the viscous effect, becomes more and more significant, slowing the flow down. And because of that, the drag force actually decreases the further you go on. And in this case, in case A, you have actually double basically the leading edge, right? So that's why it actually has more drag compared to your configuration B. Now let's move on to their second problem. Okay, so this is actually a pretty interesting one. A hydrofoil. They're basically kind of like airfoil, but in water. The idea is that they actually kind of work similar to airfoils in in the sky, the wings of an airplane. They give you a lift. But in this case, you can just treat it the same as an airfoil, which for the scope of this course, we can simplify into a plate, making the problem even easier. Uh, this is unfortunately given to us as imperial. We're not going to change it to metric. You're going to run into imperial units problem in your final. So let's take this as a practice and solve it as a imperial unit approach. You can still change it to metric, but when you do that, the number gets pretty ugly. So our 4 steps guide, but let's write down some of the basic info. L is equal to 1.2 feet. Now it says 6 feet wide, so B is equal to 6 feet. Now let's say this is an isometric view. The flow is coming into that way. That is your B, your thickness. That is your L. If you look at it from a side view, you're only gonna see the length, right? You don't see the B because it's into the page. For this problem, we're simplifying it into a flat plate. We're given their inlet velocity or friction velocity, 40 feet per second. Density, 1.99 slug per feet cube. This is new. This is your kinematic viscosity, which is equal to rho divided by mu. These are different. Equals 0.00011 feet squared per second. Make sure you know which is which. Do not divide your nu. This is pronounced as nu. This is pronounced as mu. Do not confuse your nu with mu, your dynamic. Yeah, sorry, your kinetic viscosity and your dynamic viscosity. I hope I didn't mix that up. Yeah, I do not want to come back and record everything just because I mixed those two up. Uh, Now, step guide, Reynolds number. So step one, RE is equal to rho UL divided by mu or UL divided by nu. L is 1.2 feet. V or U is equal to 40. 40 times 1.2 divided by 0.000011, which give us 4.36 times 10 to the 6th. There's actually a good way to check if you use the right viscosity. Basically conducting a quick dimensional analysis. Velocity feet per second. Length is feet. Viscosity, there we're given the unit, feet square per second. Everything cancels out, so that's a good way to check that we have used the right unit. Sorry, not the right unit, the right viscosity. So Reynolds number is 4.36 times 10 to the 6. That's bigger than 10 to the 6, so we're gonna say it is turbulent. So step 2, we're gonna find drag coefficient. Now, because it's turbulent, we're using the other drag coefficient equation, but it's still a function of Reynolds number. So finding a Reynolds number surface does two purposes. Allows us to know which drag coefficient. Sorry, the Reynolds number allows us to know which drag coefficient equation to use, but also to calculate the drag coefficient itself. Plug the numbers in, you're gonna get 4.39 times 10 to the -3. Quite low actually. That brings us, well, step 3, the area is just the top down area, which is L times B. Step 3, A is equal to L times B. Bringing us to step 4, finding the FD. FD is equal to half rho A CD V squared. Plug all the numbers in. V squared, 40 squared. And that's gonna give you 40-pound force. Voila, great. You can move on to the next question or the next part. Not quite. Funny enough, when I did this, I was actually looking at I finished it and I double checked the solution, and the solution is actually 80-pound force at the total. I made the rookie mistake of forgetting to multiply it by second, right? And this is a plate. Well, we're treating it as a plate, so we do have to multiply it by 2 because it's asking about the overall drag. It's not just asking about drag for one side. So yeah, 80 pounds forced, multiplied by 2. Again, I cannot stress how easy it is to forget that step, and it's a painful way to lose 2 marks or your final answer just because you forgot to multiply it by 2. So I think that gives us a solution for uh, I forgot to find the boundary layer thickness, but we can do that now. Um, so we found a part B. There are drag force for a turbulent smooth wall. So to find the boundary layer at the end of the plate, we're just gonna use our delta divided by x equation equals 0.16 divided by RE to the power 1 divided by 7. X becomes the length of the plate because it's asking us at the end. So 1.2 times 0.16 RE power 1 divided by 7, which give us 0.216 feet. Let's quickly double check the math. Huh. Something didn't check out. Okay, never mind. I just punched the wrong number. Oh wait, no, I did made a mistake. Sorry. 0.0216 feet. Uh, which is roughly a quarter of an inch. 12. Yeah, it's roughly a quarter of an inch. Sorry about that. Yep. 0.0216 feet. That's your boundary layer height. Might not sound like much, but this is in water, so this is actually somewhat significant. Now that's the solution to technically part A. That's the solution to part B. Uh, that brings us to part C, which is I think the hardest part of this question. So they're asking us what happens if there's a laminar turbulent flow that's basically transitional, well, with an RU crit of 5 times 10 to the 5. So basically, we have to update our drag coefficient. Because remember, transitional flow, we have other equations, different equations to calculate it. Your IE transition is equal to, what's it, 3 times 10 to the 5, right? Let's double check. Yep, sorry, 5 times 10 to the 5. So your CD equation becomes the other one that we have looked at. So we are going to basically use the first equation of CD equals 0.031 divided by REL 1 to the power 7 minus 1440 divided by REL. If they tell you that their RE trans is 3 times 10 to the 6, then you use the second equation. CD equals 0.031 RU to power of 1 divided by 7 minus 1440 divided by REL. Let's actually plug the numbers in. Remember, this is not the same one. The RE trans is just for reference which equation to use. The Reynolds number is still what we calculated before, which is 4.36 times 10 to the 6. Mm. 1440 divided by 4.36 times 10 to the 6. Our CD becomes 3.16 times 10 to the minus 3. Let's have a quick comparison. So compared to the fully turbulent one, this actually kind of reduced a little bit, just a little bit. Plugging it in, that's gonna give us an FD of half rho A V squared CD equals 36. Oops, not Newton, pound force. Again, multiplied by 2. Don't forget about that. That gives us 72.4 pound force. FD total. Voila. There goes part C. Right. let's move on to the third question now. Not sponsored by Popeyes, but I do like the wings, the bone-in ones. So we have a pickup truck. In this case, the pickup truck itself, not the plate, the pickup truck, has a drag coefficient times area of 35 feet square. Um, Again, CD drag coefficients dimension as why a unit is just feet square. There's a good example of what happens when they have a very complex geometry. So they just give you the area and the CD combined together. We're asked to calculate horsepower. Oh yeah, imperial units again. It's a good idea to get comfortable with working with imperial units. 55 miles per hour. It says clean. That just means um without the plate. And then also with the actual sign installed and with a rolling resistance of 150 pound force. The idea with the rolling resistance is that when you have your car, in order to prevent it to slip, so if it's going that way, to prevent slipping, there's a friction. So that is basically your rolling resistance. It basically acts in the same direction as your drag force. Looks like a pickup truck. So let's do part A. At the is equal to half rho A v square CD. CD8 are given, so just half density of air 0.00238 slug per V cube. V, we have to change it from 55 miles to per hour to feet per second, which is equal to 80.7 feet per second. Again, half that on your crib sheet, similar to how you have like from kilometer per hour to meter per second. Um, 35 and then 80.7 squared. That's going to give us 271 pound force. Now we have a rolling resistance of 150 pound force. So technically, this is the answer for part A. Actually, sorry, no. You actually have to combine it with the rolling resistance as well. So FD total is equal to F rolling plus FD drag. Call this FD drag, which is equal to 150 plus 271, 421 pound force. Probably shouldn't call it total. I should probably call that clean. Because the total would implies that includes the plate, which is part B. There we go. Now part B, that's where we get the actual total. It's equal to what we calculated in part A plus FD for the plate, or sorry, I shouldn't call it plate, I should call it sign. Plate implies that it's laying flat down. So you actually need to go into a table to find the drag. This can also happen in an exam where it's not given, or it will be included in your A sheet, a simple table For geometry, let's see if it's for like a circle, there'll be a sheet as well, or sorry, a table in your A sheet. Now, the table in this case is from the textbook. We need to base it on your aspect ratio. So B divided by H, in this case, we have roughly 2. Uh, you can use linear interpolation. In this case, excuse me. In this case, we're just gonna roughly estimate it to 1.185. You can linearly interpolate it, but I'm just doing a guesswork. It doesn't really change that much. Increases what, a couple percent. So our FD sine half rho A B squared CD. The density stays the same, 0.00238. Our area updates because it's the area for the sine, right? That becomes 6 feet by 3 feet. B stays the same, 80.7 squared, CD 1.185. Giving us 165-pound force. Combine it with our total. FD total is equal to 421 plus 165. And voila, we have a total drag of 586-pound force. We don't have to multiply it by 2 in this case because the plate is perpendicular. It's a different geometry compared to a flat plate that is horizontal to where your flow is coming in. The drag force in this case has already account for the effect, so we don't have to look for it. So I think that about wraps it up for this supplementary tutorial section. The textbook solutions are included in the slide deck. Yeah, feel free to add me on LinkedIn. But if you have questions about the content of the tutorial or the material, just email me. And voila.